Okay, everybody, thanks for joining us. So you've made it to the last session. Hopefully you've learned a lot throughout the day. You're here to see the presentation, Don't Muddy the Waters, Construction BMPs for Bridge Rehabilitation. Again, just a reminder, this is also a virtual platform, and those who are online, you can submit your questions through the Q&A. And so now I'll just go ahead and introduce our speakers. We have Fiona van Ammers. She brings 22 years of experience in planning, design, and permitting of infrastructure development projects throughout Hawaii. She is both a licensed civil engineer in the state of Hawaii and a certified professional in stormwater quality. She is passionate about delivering equitable, sustainable, and clean water for Hawaii. And then we also have Andrea Cheung. She is also a licensed engineer and the Hawaii Civil Portfolio Design Leader at Brown and Caldwell. That's a big title. Her focus is in design, project delivery, and management. She leads large civil infrastructure design projects and has experience with local stormwater BMP standards. So let's go for it, guys.
Thank you, John. Good morning, everybody. Thanks for joining us to talk about construction best management practices for bridge rehabilitation projects. I realize it's almost lunch. My stomach is growling, so we're going to try to keep things moving. Before we get started, however, I wanted to kind of set some intentions for today. This presentation is meant to share what we know and what we've learned about BMPs and good practices for them. You're going to see some photos of good BMP implementation and not so good BMP implementation. And this is not to point fingers at anybody, but really just to learn from each other. And this discussion should provide you, whether you're an engineer or a contractor, some general guidelines to get started in implementing BMPs for bridge rehab. The agenda today, we'll go over the why. Why is it important to do good BMPs? We'll talk about common construction activities and the pollutants that they generate. And then Andrea will talk about how to prevent pollutants from getting into our waterways, to either prevent generating them or capture them. And then we'll review the main takeaways. Why do we care? Well, like much of our buried infrastructure, our bridges and culverts, which convey surface water, are reaching the end of their useful life. Many are nearly 100 years old. And so the state and the counties are investing money in condition assessment, rehab, and replacement. Contractors have the great challenge of implementing improvements such that human health and safety is protected, not just on the job site, but also downstream of the job site. Before I dig in on this slide, I'd like to poll the audience. Raise your hand if you like to surf. Okay. How many of you guys paddle canoe? Nobody? Okay, me. How many of you guys take your kids to the beach, or maybe your kids like to swim in some of our freshwater streams? Yeah, Yale Valley, right? Okay. And who here likes to fish or likes to eat fresh fish? Everybody, right? Okay. So then we all care about having clean water, whether it's our streams or our ocean. And what's really important here is if you look at this middle picture, this is the Olivine Canal. Has anybody seen this sign? Yeah, it says, no swimming, no fishing, exposure to water may cause illness. So nobody wants that. And construction activities can produce pollutants that can get into our waterways. And when those pollutants get in our waterways, they damage our reefs, they damage groundwater, and they damage other natural resources. So contractors play a critical role in mitigating the generation of pollutants and preventing them from getting in our waterways. All right, another quick poll. Who here has extra pocket money to pay regulatory fines? Okay, no one, right? Because cost of living in Hawaii is already really high, and so we're just struggling to live. Well, water quality is regulated by federal law, and violations of a federal law can result in fines. The law is commonly referred to as the Clean Water Act, and it has a lot of sections to it. I'm not going to get into the details of that, but it's really important to know that contractors are responsible for preventing pollution into our waterways. The Department of Health, the Army Corps of Engineers, the counties, and the states have the authority to fine you. Jamie just did a presentation, and she mentioned that inadequate BMPs is the most common violation that she finds. And the fines can be up to $35,000 per day per violation. All right, so let's talk about some of the common construction activities and the pollutants that can come out of that. So first thing that we often do is demolition. Demolition can produce dust and other material waste. You will likely have paving. You may be milling or grinding pavement, possibly putting down new pavement. Both activities can create dust and waste. Probably will be doing some deck work. So installation and removal of steel and concrete, removal and installation of coatings and hot work. And all of these activities have the potential to create dust and trash that includes compounds like hydrocarbons, lead, mercury, silica, and other toxic materials. What often happens is that you create a bunch of dust, it will land in the waterway, and then it will leach into the water. Also, trash gets left behind, it rolls into the waterway. So it's really important to prevent that. It also should be noted that sometimes the materials that come out of a construction site, they will get into the soil that's immediately adjacent to the bridge. And later you'll have erosion due to a storm, or maybe you're doing other activities along the stream bank or the stream bed. You're going to get sedimentation, and that can get in the water. So pollutants inhibit the growth of aquatic vegetation, and they're harmful to human health. And at a minimum, they cause aesthetic problems. All right, so probably going to do some concrete work. Concrete work creates dust. It creates concrete washout. This photo here is deficient BMPs. We've got concrete rubble on the pier and on the sand. Concrete it's very caustic. It has a very high pH. Not when it's cured, but when it's in a concrete slurry, it's really not good for waterways. If you're pouring that into a stream, you're basically putting Drano into a stream. You'll probably have some painting. Painting can produce dust and paint chips. We all know that some of the older bridges may have lead paint. Lead is very harmful for human health, particularly children. And you're probably going to be working on abutments and piers. Those are often next to or inside of the stream bank or the stream bed. So a lot of the activities that you'll do have the potential to create sediment. Sediment can smother habitat in the water. Basically, the sun can't get into the plants. They will not grow. And then the fish don't have plants to eat, et cetera, et cetera. Sediment also carries nutrients like phosphorus and nitrogen. When that gets into the water, we see algae blooms. When algae blooms die, they decompose and they use the oxygen in the water, takes all the oxygen out of a waterway, and you basically are suffocating fish. All right, and then lastly, there's common activities that you're going to see not just on your bridge rehab, but in all your construction sites. You're probably going to have heavy equipment. That heavy equipment can leak oil, grease, and chemical fluids. It can track sediment. We talked a little bit about what sediment can do. You'll have staging and stockpiling. Those have potential pollutants within them. And then you might also be doing some relocation or rehabilitation of pipelines that are hanging from the bottom of your bridge deck. There's a potential for spills from that. Definitely don't want to break your sewer pipe and have it drain into the stream. So basically, all of these activities that you're doing at your construction site can generate pollutants, oil, pesticides, chemicals, and heavy metals can come out of that generated pollution. And high levels of these pollutants in our water can really affect the ecosystem and really cause problems in our fresh water. So we really need clean fresh water to drink, for agriculture, and to play in, right? So we don't want to muddy the waters. So really, it's our kuleana as engineers and contractors to do our best to prevent these pollutants from getting in the water. Now I'm going to hand it over to Andrea.
Thanks, Fiona. Now I'm going to go over some steps that we can take to prevent or capture those pollutants from entering the waters and prevent them from muddying up our streams, rivers, and oceans. The first I'm going to go over are administrative and work controls, which occur prior to the start of construction. Next, we'll go over water or on-land best management practices, also known as BMPs. And last, we'll go over in-water BMPs themselves. As a note, HDOT and the Federal Highways Administration have created a guidance document that will actually go over much of what I'm sharing. This guidance document is still in draft form and has yet to be publicly released, but I believe it will be released shortly, or you can talk to your local HDOT rep. First, we'll go over administrative controls. What exactly are these? During the design stage, engineers will design BMPs that will match the project work at that specific site. These BMPs will go into contract documents that are required to be followed during the course of construction. These also include specifications, such as the HDOT 2005 Standard Specifications for Road and Bridge Construction, Section 209, which goes over temporary water pollution, dust, and erosion control. In this are requirements for the creation of a site-specific BMP plan, or if your work area is greater than 1 acre, then a stormwater pollution prevention plan or a SWIP. Within these plans, there would be information for debris containment, temporary diversion, erosion and sediment control, training of personnel, and regular inspection and maintenance of BMPs, which must be followed throughout the course of the project. Administrative controls also include such considerations as scheduling and staging. Example of scheduling considerations is to do construction work during the dry season when stream flows are low, or to avoid fish migration or spawning seasons when you would need more water in order for aquatic life to propagate. Some staging considerations are generally to keep your equipment, your construction vehicle, your equipment, and stockpiling away from water bodies to avoid for rainwater to wash pollutants and sediment into the streams. Some considerations for this is to make sure that your staging is above the high stream mark. For streams, that would be the ordinary high water mark, or for tidal influence waters, it would be, I believe, the mean high water mark. To keep your staging and stockpiling locations at least 50 feet from the edge of stream banks or shorelines. To use BMPs for your staging and stockpiling, such as covering your stockpiles or drip pans under equipment to capture oil and grease. All of this can be done to prevent pollutants and sediments from entering the stream prior to even working on the bridge. Lastly, are work controls. And work controls is the training of individuals within the contractor's team to install, inspect, and maintain BMPs before and during construction. The team will generally be certified to manage all BMPs and to do weekly to monthly inspections and any cleanup of accumulated pollutants or repair, damage, or replacement to BMPs. However, everyone at the job site should be made aware of what the BMPs are and what they might look like if they're damaged and need to be repaired or replaced, and who they should contact so that it is done quickly. Next, we'll go over overwater or on-land options for BMPs. I won't be able to cover everything as there are a large variety of options, but I'll go over some of the common ones. Oops. So one common one is to use tarps, platforms, or floating barges underneath the bridge to catch any debris from demolition or work before it even hits the water. Depending on the type of work, the tarp or platform can be hung from the bridge or supported in the water like shown in this picture. For the platform, it should extend beyond the drip line of the bridge so that it can capture any of the rainwater or stormwater from above. Concrete or other debris that is falling can actually bounce off of your tarp or platform and into the water. And so you want to make sure that you account for that when you're creating designing the width of the platform. And also, as shown in the second picture, maybe adding sides to prevent the bouncing from happening into the water. Platforms and scaffolds should always be designed by a licensed structural engineer, they would take into account the loads from the platform itself, any people or equipment that are standing on the platform, and the weight of the debris that's expected to fall from the bridge onto the platform. If the bridge is too low to install a platform, a floating barge is also an option and can be anchored underneath the bridge work. For a floating barge, you would want to consider the size and weight of the debris that would be captured, as you would need to make sure that your freeboard doesn't go below the water line. The last part of this is that often bridges span across banks, so it's not entirely water entirely underneath. And so you would come up with different BMPs to help capture debris from hitting the stream banks and possibly rolling into the stream. Other methods for preventing pollution from pollutants from entering the stream include just means and methods. For example, if you're doing demolition work, saw cutting releases less debris than other forms of demolition and can be vacuumed or collected using negative pressure dust collectors. You can also include attachments on construction vehicles and equipment to capture small debris. And don't forget about your on-land BMPs. Most bridges have scuppers and down drains, which are basically openings to allow rainwater to flow down to the stream, or storm drains on either side of the bridge in order to allow water to flow through. These need to be protected with BMPs as well. Finally, we're going to go over in-water options. I'm going to break this down to 4 topics shown here. So first are general considerations, which are going to apply no matter which in-water means or methods that you choose. All BMPs are first and last. Just keep that in mind, first and last. That means that you install them before construction and you take them away after the end of construction. If you're using materials inside the stream for BMPs, you want to make sure that they are inert, non-toxic, non-hazardous, and close to neutral pH so that you don't mess up the downstream water chemistry. BMP design and installation and maintenance should take into account weather and tide events, such as flash floods or king tides. If you're working within 50 feet of state waters or undisturbed natural buffer less than 50 feet is used, double perimeter control BMPs are required to be installed and spaced a minimum of 5 feet apart from each other. And finally, don't forget about the aquatic life and vegetation. There was a recent project that happened in Maui just a few years ago where they were installing a fish ladder in Wailuku Stream. In order to safely install this fish ladder, they had to drop the stream flows. Well, they did this project in late summer, early fall, when water levels were already low. When they dropped the flows, what do you think happened downstream? And this is a question for the audience. Can anyone tell me what happened downstream when you dropped the water flows during an already dry season? No more water? Close. So they had hundreds of native Opu fish kill. There was not enough water to support the fish downstream, and they built the ladder to help the fish, but instead ended up with hundreds of them who died. So make sure to take that into account as well. Another thing to consider prior to actually installing your in-water BMPs is to install any stream bank stabilization. Stream banks are often affected by doing in-water work. Can anyone in the audience tell me how stream banks can be affected if you're doing in-water work? Any thoughts? All right, well, first, if you need to bring down vehicular equipment to the stream to do work, you would probably construct a temporary ingress egress. So that's basically gravel, not gravel, but using larger rocks to create a temporary road down to the stream. If you're doing any abutment rehabilitation or replacement, or if you're doing scour mitigation along the banks, you would also be affecting the stream. So temporary stabilization for stream banks needs to be installed prior to doing any in-water work. And then similar to the rest of BMPs, they will also be removed after everything else is complete. Often though, when you're doing temporary stream bank stabilization, you probably need to install permanent BMPs as well to stabilize the stream banks long-term. And so you would remove temporary stream bank stabilization, install permanent stream bank stabilization, and then ensure that if you're using vegetation or other methods, that particular stabilization takes over a series of months. Common stream bank stabilization BMPs include compost filter socks, silt socks, vegetation, which I believe vegetation of riparian areas, which is preferred just for the natural restoration of streams, riprap, and retaining walls. So finally, we'll go over some in-water BMP work. And when you're doing in-water work, there's basically two methods to this. Either you can capture sediment or pollutants as they're already in the water and prevent them from flowing downstream or spreading. Or you can isolate out your work area, which means to block out water from entering that area. So that way your pollutants don't fall into the stream or carry downstream. And also so that you can maybe collect them. First, we're going to go over sediment capture. So there's a few technologies for sediment capture, which include perimeter erosion controls, turbidity or silt curtains, and sediment traps. Perimeter controls like filter fabric are fairly good in calmer water and relatively inexpensive. What I think everyone's pretty familiar or commonly seeing are turbidity or silt curtains. And these are used when it's fairly unavoidable that sediment or pollutants are going to enter the stream or river or ocean. They are designed to capture suspended sediments floating in the water while letting the rest of the stream flow underneath. They are often used in slow-moving water bodies or to isolate nearshore work, but they can also be used in tidal waters with some wave action. These are some example details for installation of turbidity curtains at construction sites. The material is often a vinyl material with a float attached on top and anchored in a partial ring around your project area. The top left is a detail for calm water installation, while the bottom left is a detail for more wave action or higher tides or winds. There are generally 3 different types of turbidity curtains, and they vary depending on your water conditions, calmness of water, velocity, turbidity, etc. This is just a couple of examples of turbidity curtain deficiencies on recent HDOT projects. Can anyone find the turbidity curtains in these? Can you guys see them? Are they supposed to be where they're supposed to be? No. Where are they supposed to be? Anyone from the audience? In the water, that's correct. So one in the water, anchored correctly and staking out for protection. In these 2 examples, it's unclear if they were damaged or if they just got washed ashore, but they should be replaced immediately once removed. Okay. And the last bit of sediment capture is sediment traps, which I just used to broadly categorize a large number of options that you can either commercially buy or construct. Often sediment traps are used to either collect directly or can be used as part of stream diversion, which we're going to go over next. So again, to reiterate, stream diversion is when you want to divert water around your project site to avoid pollutants being carried downstream and to hopefully be able to capture those pollutants via another method like a tarp or using perimeter controls. There are three common types of stream diversions. One is pump diversions, which is when you pump upstream water around the job site and down into downstream water. This is often used when your stream is fairly a shallow slope. Another option is to use a pipe or flume diversion. And this is better used if your stream does have some slope and you can use gravity to carry the water around. The last one is excavation or dam diversions, which can redirect the flow of water to a side stream or channel, or to maybe one side or the other of the stream itself if it's large enough. These three methods are not mutually exclusive. You can combine them with each other and vary them depending on the different parts of the project that you're working on. Some other notes are that smaller streams sometimes need to be fully isolated as they're too small to do a partial diversion, whereas larger streams, maybe you can only do a partial diversion isolation, and those should be taken into account when you're designing your BMPs. When constructing a diversion channel, it is recommended to start from downstream and work your way upstream. It is also recommended to pass the water from upstream through a sediment capture device or a settling device before discharging it downstream to get rid of some of those pollutants and sediments. In addition, velocity dissipation devices are good at the entry and exit points of the diversion to slow down the water and prevent excess erosion. All of these stream diversion methods require a barrier to isolate the water and force the diversion. Stream isolation methods, which are used, are often temporary berms, dikes, and cofferdams. These are partially or fully watertight structures and can be made of sand, rocks, concrete, steel, wood, earth, vinyl, other materials. Materials and structures that would be chosen depend on the height of the water body, the velocity of the water body, any currents, and scour conditions that are expected under both normal and high flow conditions. We're just going to go over a couple of those stream isolation methods in greater detail. The first is pretty common. I'm sure everyone's familiar with the sand or gravel bag. These are layered on each other in the water until they are above the high water mark. These aren't necessarily the most water impermeable, and so sometimes a plastic sheet is tucked in around the plastic bags to prevent water from seeping through. Another common method is to use concrete, often in the form of jersey rails or K-rails. These are usually used in conjunction with gravel bags as well at the toe, and are often wrapped in plastic as well, because again, similar to sandbags, they're generally only partially or good for partial dewatering. However, jersey rails and K-rails are also good for creating a sediment deposition area or for stream bank stabilization, so multi-purpose. If you're sitting in on the Army Corps of Engineer presentation, they mentioned porta dams and aqua dams, which we're going to go over next. Commonly known as the porta dam, which is the commercial name. These are basically impermeable membranes or plastic that are anchored into the stream to create a barrier. These are often bolted in to a concrete foundation, a steel support, or held in place by gravel berms. This is a water dam, more commonly known by its commercial name as aqua dam. These are geotextiles, plastics, or rubber bags that are filled with water to be above the high water mark. And sheet piles. Sheet piles are most often used for flow dewatering. They have interlocking edges that are driven into the ground with vibration equipment. They are often made of steel, but can also be made of wood, precast concrete, vinyl, or aluminum. These are completely watertight and are often used for pier footing or abutment excavations. Driving piles into the ground can disturb the local aquatic wildlife, so sometimes it's recommended to use an air bubbling system to prevent that from happening. All right, takeaway points of this presentation. So number one, the point of all of this is to prevent pollutants from entering the waters that we swim in, that we fish in, that we take our kids to. Pollution prevention, beyond for our own personal gain, is regulated by federal laws and administered by state and federal agencies. There are different methods for addressing this. First being administrative and engineering work controls, which are done prior to construction, or BMPs on land, above water, or in water during construction. It is important for contractors to train specific individuals and teams to document and perform regular inspections and maintenance on these BMPs, and is generally regulated by their site-specific BMP plan that has been approved. And finally, just as a quick reminder, this is the draft guidance document that I mentioned earlier that goes into most of what I discussed in much greater detail, and will hopefully be released publicly in the future, and or can be obtained through someone that you're working with at HDOT. Thank you, everyone. Are there any questions?
This is more on the front end. When you get the permit, when you're trying to calculate disturbed area, do you have to calculate the bridge deck as in addition to all the area under the bridge deck? So like that is doubled.
I think you're referring to the NPDES construction C, Appendix C, which is regarding more than 1 acre of disturbed area. I actually don't know the technical answer to that, but I guess the point that you're trying to make is that if you are over 1 acre, you trigger an NPDES C permit. And thank you, Bob, for what you shared, because we were trying to avoid the discussion about permits because it is very challenging. But as a general rule, all the area that is disturbed on a construction site, whether it's the infrastructure or the staging or installation of the BMP, that all has to count to the total acreage.
Yeah, I was more talking about the difference between, you've got the bridge deck and that's an area, and then you're working under the bridge deck. So if you have to double count that.
Yeah, so I think, John, it would count because it's separate area. But yeah, if you're touching soil, basically, or you have construction equipment or other, Janice might have the answer to it.
Installed under the bridge as a BMP for your 401 and 404 permit. If that's all regulated by the Army Corps and DOH under a 401 permit, if you have a 401 or a blanket permit, it's not typically under the Appendix C permit, although the bridge deck would be, or whatever you're doing with the roadway.
But even if you're grading a stream bank or stream bed.
Asking about
stream bed.
Okay. Under the
Yeah, that's a good point. Yeah, the in water stuff is going to be Army Corps.
Take some soil, install your BMP.
Right.
You put the BMP just on the top of the ground or in the water, that wouldn't count as part of Part C.
Yeah, for sure. Whatever you're doing.
Yeah, it depends on what activity you do.
So did we answer the question? If you're touching dirt, that would count towards the 1 acre. But the in water BMP itself, if it's floating on the surface, that would hanging, right? That would not count.
Looks like we don't have any online questions. So are there any other questions in the room? Okay. All right, well, thank you guys so much for presenting today. We really appreciate it. A couple reminders, if you haven't got your parking validated, you should do that on the way out and over by the same booth that you checked in. And other than that, we just thank you guys for attending today. And I'm sure if there are a few minutes, if you didn't want to ask your question openly, you can come up and ask questions. But otherwise, have a great rest of your day. Thanks.